So in question 8, we are given this complex number, and in part A1, we need to show that the argument of this complex number is simply theta. So we need to remember that the argument is simply equal to the arctangent of the imaginary part divided by the real part. So sine 2 theta over 1 plus cosine 2 theta. So we need to start using some trig identities here to simplify what is inside of this arctangent. So sine 2 theta is simply 2 sine theta cosine theta. And we can also write cosine 2 theta as 1 plus 2 cosine squared theta minus 1. Now on the bottom, the 1 will cancel out with the 1. And then this cosine squared will cancel out with, so this 1 will cancel out with this one. So we just have 2 sine theta over cosine theta. So indeed, that is arctangent of tangent theta. And well, we know the inverse of a function is just what is inside, so this is just theta here. All right, and then part 2, we need to show that the modulus or the length of this is 2 cosine theta. So we can use Pythagoras to express the length of a complex number. So this is 1 plus cosine 2 theta squared plus sine 2 theta squared. And again, we need to use some trig here. So this will simply be 1, well, we can rewrite cosine 2 theta again. So this will just be 1 plus cosine 2 cosine theta squared minus 1. This is still squared. And similarly, sine 2 theta is 2 sine theta cosine theta squared. Okay, and well, what we could do now is, well, the ones will just cancel out again. So that's nice. So we can rewrite the whole thing as just 4 cosine to the 4th theta, and then plus 4 sine squared theta cosine squared theta. We can factor out the cosine squared. So what we are left with is just the cosine squared theta plus sine squared theta. And very nicely, we see cosine squared plus sine squared is just 1. So what we're left with is under the root 4 cosine squared theta. We can just take the square root of that, and so we are left with 2 cosine theta.